The source of magnetic field.
Hello everyone, I'm Adrian Lagsub and I will discuss the Biot-Savart law. In chapter 29, we discuss the magnetic force exerted on a charged particle moving in a magnetic field. To complete the description of magnetic interaction, this chapter explores the origins of magnetic field moving charges. We begin by showing how to use the law of Biot and Savart to calculate the magnetic field produced at some point in space by small current element. This formalism then use the calculate the total magnetic field due to various current distribution. Next, we show how to determine the force between two current carrying conductors leading to the definition of Ampere. We also introduce Ampere's law, which is useful to calculating the magnetic field of a highly symmetric configuration carrying a steadily current. This chapter is also concerned with the complex processes that occur in magnetic materials. All magnetic effects in matter can be explained on the basis of atomic magnetic moments, which arise both from the orbital motion of electrons and from an intrinsic property of electrons known as spin. So we have here the mathematical expression of the Biot-Savart law. So dV is equal to mu sub 0 over 4 pi times I ds cross product r hat over r squared. So dV stands for magnitude field. Mu sub 0 stands for permeability of free space. I is current in the length element ds, and ds is a length vector. R hat unit vector pointing from ds to dB. And the r squared is distance from ds to dB. So we have here the example 30.1. Consider a straight wire of carrying a constant current I and placed along the x-axis as shown in figure 30.3. Determine the magnitude and direction of the magnetic field at point P due to this current. So we use the equation Biot-Savart law. dV is equals to mu sub 0 I over 4 pi times ds cross product r hat over r squared. We do cross product. We use sine of the angle ds vector and r hat vector. Sin gamma is equals to sine 90 minus theta or equals to cos theta. So the d is equals to dx and the r hat here is the cos theta over r squared inversion of k hat. So note that tan theta is equals to negative x over a. So we use the cross product. So x is equals to negative a times tan theta is equals to negative a tan theta. So the derivatives of x is x, and the derivatives of negative a tan theta is negative a secant squared theta d theta. So cos theta is equals to a over r. So again, we do the cross product. So r is equals to a over cos theta. So we know that the identities of 1 over cos theta is sec theta. So we substitute the value of dx, which is negative a secant squared theta d theta. And then we copy the cos theta. The value of r squared is a squared secant squared theta. And then, we cancel the negative a secant squared theta and a squared secant squared theta is equals to negative mu sub 0 I over 4 pi a times cos theta d theta. The magnetic field is equals to negative mu sub 0 I over 4 pi a times the integration of cosine theta d theta from theta 1 to theta 2 is equals to mu sub 0 I over 4 pi a times to the integration of cosine theta, which is sine theta, from theta 1 to theta 2. Substitute the upper limit minus the lower limit. So it's equals to mu sub I sub 0 I over 4 pi a times sine theta 2 minus sine theta 1. Note that theta 2 less than 0 degree because clockwise direction. Theta 1 is equals to negative pi over 2 and theta 2 is equals to pi over 2. The value of theta 1 substitute here and the value of theta 2 substitute here. So mu sub 0 I over 4 pi a times sine theta over 2 minus negative sine pi over 2. Then magnetic field is equals to mu sub 0 I over 4 pi a times 2 1 plus 1. So sa tagal yung 1 plus 1 natin. So yung value yung value ng sine theta over 2 is 1. So ito siya yung value niya. And ito rin yung isang 1. So it's equals to mu sub 0 I over 4 pi a equals to 2 times 2 is equals to mu sub 0 I 2 pi a. The magnetic field at 0 due to the current in the straight segment AA and CC is 0 because the DS is parallel to R. So it's parallel to R hat along this path, which means that DS cross product R hat is equal to 0. For these paths, therefore, we expected the magnetic field at 0 to be 0 only to the current in the curved portion of wire.
Gusto mo ng lemon?
Yes. Each length DS long paths AC is the same distance A from 0.
Adriana!
0.
Oo, sige.
And the current in H contributes a fifth element dB direct into the page at 0. So, furthermore, at every point on AC, DS is perpendicular to R hat. DS cross product R squared is equal to DS. Therefore, from equation 30.1, find the magnitude of the field at 0 due to the current in an element of length ds. Length ds. So, dB is equals to mu sub 0 over 4 pi times I ds over a squared. Integrate this expression over the curve path AC. Nothing that I and A are constant. So P is equals to mu sub 0 I over 4 pi A squared times integration ds is equal to mu sub 0 I over 4 pi A squared times S. From the geometry, note that S is equal to A theta. So we substitute the S to A pi. Is equal to mu sub 0 I over 4 pi A times theta is 0. Example 30.3. Magnetic field on the axis of a circular current loop. So, consider a circular wire loop of radius A located in the YZ plane and carrying a steady current I as the figure 30.5. Calculate the magnetic field at an axial point PA distance x from the center of the loop. In this situation, every length element ds is perpendicular to vector r hat at the location of element. Therefore, for any element ds cross product r hat is equal to ds times 1 sine 90 degree is equals to ds. Furthermore, all length elements around the loop are at the same distance r from P, where r squared is equal to a squared plus x squared. So, use equation 30.1 to find the magnitude of dB due to the current in any length element ds. dB is equals to mu sub 0 I over 4 pi times ds cross product r hat over r squared is equal to mu sub 0 I over 4 pi times ds over a squared plus x squared. So, find the x component of the field element. So, dB sub x is equals to mu sub 0 I over 4 pi times ds over times cos theta, and then integrate over the entire loop. So b sub x is equal to integration of dB sub x is equals to mu sub 0 I over 4 pi times integration of ds cos theta over a squared plus x squared. From the geometry, evaluate cos theta. Cos theta is equals to a over a squared plus x squared raised to the power of 1/2. So b sub x equals to mu sub 0 I over 4 pi close surface ds over a squared plus x squared times a over a squared plus x squared raised to the power of 1/2 is equals to mu sub 0 I over 4 pi times a over a squared plus x squared raised to the power of 3/2 close surface ds. So, dx is equals to mu sub 0 I over 4 pi times a over a squared plus x squared raised to the power of 3/2 times 2 pi a is equals to mu sub 0 I a squared over 2 times a squared plus x squared 3/2. So we have here the equation of the magnetic force between the two parallel conductors. The field B2 due to the current in the wire 2 exerts a magnetic force of magnitude F sub 1 is equals to I sub 1 L B sub 2 on wire 1. So F sub 1 is equal to I sub 1 L B sub 2 is equals to I sub 1 L times mu sub 0 I sub 2 over 2 pi A is equals to mu sub 0 I1 I2 over 2 pi A times L. So we have here the example 30.4, suspending a wire. Gravitational force sub B is equals to 2 times mu sub 0 I sub 1 I sub 2 over 2 pi A times L times cos theta K is equals to mu sub 0 I sub 1 I sub 2 over pi A times L cos theta K. So find the gravitational force on the levitated wire. So gravitational force sub G is equals to negative mg k hat. Apply the particle and the equilibrium model by adding the force and setting the net force equal to 0. So summation of gravitational force is equals to gravitational force sub B plus gravitational force sub G is equals to mu sub 0 I sub 1 I sub 2 over pi A times L cos theta K hat negative mg K hat equal to 0. Then solve for the current in the wires on the ground. So I2 is equals to mg pi A over mu sub 0 I1 I sub 0 L cos theta. Substitute numerical values. So I sub 2 is equal to 0.400 kilogram times 9.80 meter per second squared pi times 0.10 meter over 4 pi times 10 raised to the power of negative 7 Tesla meter per ampere times 10 ampere times 10 meter cos 30 degree is equal to 113 ampere.